Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, today we will start discussing a new session called probabilistic modeling. From the name, what is the main concept that we need to know to discuss this session? Probabilities. Very good. So inshallah today we will review some probability and statistics principles that will inshallah prepare us for talking more about probabilistic modeling. First, what do you mean by probabilistic modeling? In the context of machine learning, when we talk about probabilistic models, we mean that we want to build models that will use statistics. In other words, we will see or we will view the learning problem as a problem of statistical inference. Of course, you are familiar with the word statistics, right? You took at least one course, and maybe also in high school you took some courses in statistics and probabilities. But what do you mean by statistical inference? Any idea? What do you mean by the word inference by itself? So inference is like prediction. Okay, you are given something or some information, and you want to after being given that information, you want to predict that something will happen or will not happen. Okay, this is in general what we call inference, and we will do that using statistical methods or statistical principles. If this is not yet clear, it will be clear inshallah today and the next lecture. Type in viewing machine learning as statistical inference problem, we will assume, as we did earlier in the course, that the training data follows a specific probability distribution. Okay? Type. I think you heard about that before, right? And we also, in the very beginning of the course, and we also assumed that, or not assumed, we realized that even if we assumed that the training data came from a specific probability distribution, we don't know that distribution. Okay, so our goal here is to try to estimate or to learn this distribution from what we have. What we have is the training data in machine learning, right? We have training data, so we will try to estimate or guess the parameters of the probability distribution from which this data was actually generated. We don't know it, so we'll just make some guessing. Okay, so this is in one slide what we will do. Of course, we will discuss the details. Now let's review some statistical principles. First one is Bayes rule. Before we get into Bayes rule, what is a probability distribution? What do you mean by probability distribution? What do you mean by a probability? Can you give me an example of a probability? Okay, that's a classical one, right? If we roll a die, so there is a probability of getting what? One of the two faces, head or tail, right? Each one has a probability. If the not head or tail, that's a coin, right? Die has 6 sides. Okay, that's the other classical examples. Sorry. So die has 6 sides, right? So if it's fair, which means that each side has the same probability, then the probability of each one is 1/6, right? Type. In this case, we have an event, which is rolling a die, and the event has outcomes. In our case, in this case, how many outcomes we can get? 6 outcomes, right? Each one is assigned a specific probability. It happened that in our example, because the die is fair, each face or each outcome will have the same exact probability, which is 1/6. Okay? When we have an event and we are assigning a probability to every possible outcome to that event, we call this a probability distribution. Okay? Type. Now, when I say that, let's take another example. If I said that the probability of getting an A in this course is what? Can you guess? Can you give is what? 0.1, 10%. Okay, very optimistic. No, you are very pessimistic actually. Let's say 20%. Okay, let's say that the probability of getting an A in this course is 20%. What do you mean by that actually? What is the meaning of that? That the probability of getting an A is 20%. What's the actual real meaning of this? How can we interpret this? Yes, Nama? If what? 2 students out of 10. So in general, if we maybe observed multiple classes, multiple machine learning classes, maybe in different times, and we looked at how many students got an A and how many didn't, then on average, we'll find that 20% of the students got an A. That's the meaning of probability, okay, or one meaning at least of probability, okay? Type. So the event here was whether the student will get an A or not. Type. Another example. If I asked you, what is the probability that it is raining today, or it will rain today? 0. Why is it 0? Huh? It's so hot today, but it's windy. Anyway, in general, if you don't know the day, and I told you we are just in Qatar, I didn't tell you any day, what is the probability that it will rain? 10%? Okay, maybe. Let's say 10%. Type. Now, if I told you today is one day of the winter days. We are in the winter season. Okay? Now, what is the probability that it will rain today? Maybe 20 or 30, right? It changed, right? Why did it change? Because there is another event, right? That we know about. Of course, there are many events, but sometimes we don't know anything about. So the best guess, and when I told you is it raining or not, it was 10% because we are not talking about knowing any information. But if I told you that this is winter, then the probability changes, right? This is exactly what Bayes' rule is trying to give us. Bayes' rule is about relating the probability of two events. Okay? Probability of two events. What is the probability of one event given that we know the outcome of the other event? So probability of A given B is equal to probability of A and B over probability of B. Now, this is called the conditional probability. I think you are familiar with that, right? So this is the probability of observing the outcome of A, specific outcome of A, given that we already observed the outcome of the event B. This is equal to the probability of both of them occurring together over the probability of the conditioned one occurred only. We call the one in the numerator the joint distribution or the joint probability. Okay, so this is the probability of observing both jointly, A and B. Okay, so in our case, the probability that it is raining, given that we are in the winter season, is equal to probability of being in the winter season and it is raining, right? That's the joint probability, right? Of raining and winter season over the probability of what? Of the winter season. Okay, this is of course might be different from just the probability of the of raining without knowing that we are in the winter season or the summer or any season. So this is Bayes' rule, relating two events together. This can also, if you look at Bayes' rule, now you can also say that probability of A and B equals to what? Equals to the multiplication of these two, right? It's the probability of A given B times probability of B, or probability of B given A times probability of A, which is the other form of Bayes' rule. P, probability of A given B, equals to probability of B given A, the reverse, times probability of A divided by probability of B. Now we call, remember when I asked you about what is the probability of reigning without knowing anything else? This is called the prior probability. Probability prior to knowing any other information. That's why it's called the prior probability. Probability of A given B, which is probability of reigning given it's winter, we call it the posterior probability. After knowing that it is the winter season, what is the probability of reigning? Okay, so this is called prior. Both are probabilities of A, by the way. But this one, without knowing anything, unconditional, the prior probability, and this one is conditioned on observing the outcome of B, and it's called the posterior probability. Okay, so this is just a revision of Bayes' rule. Any questions? Right. Now let's focus on the joint distribution. What is the definition of joint distribution? It's a probability distribution for two or more random variables. If it's just one random variable, it's just a probability distribution. If it's two or more, this is called joint distribution. Type. What do we have in this joint distribution? Now we have two or more variables. So for the example that we see in the slide now, we have three variables. We have the gender, we have hours worked, it's either less than 40.5 or greater than 40.5. And we also have the third variable, which is the wealth, poor or rich. For a joint distribution, we'll have to know or to assign a probability for every possible combination of these variables. And as you see here, how many possible combinations of these variables? How many possible values of the first one? 2. Second one? 2 also, because we have either greater than 40.5 or less than 40.5. And the third one? 2. So we have 2 times 2 times 2. We have 8 possible combinations. So you see here 8 rows. For each one row, each combination of the possible values, we have an assigned probability. If you sum all of these probabilities, you will get 1, which is always the case with any probability distribution. For any probability distribution, if you sum all the probabilities, you will get 1. And joint distribution is just a special case of a probability distribution. It's just that we model more than one variable. But still, all the probabilities will sum to 1. Okay? Type. Let's see how the joint distribution is really useful. The first thing, we can actually, using the joint distribution, we can compute the probability of any logical expression. For example, if I told you what is the probability that we will have a female that is poor, can we compute that from this table? This is a table, right? Can we compute that from this table? Probability that, let me change this. Probability of female and poor. Can we compute that from the table? How? 0.0. Can you tell me which line you are talking about? The first one, female and poor, so the first one, and third one, right? Because these are the only 2 rows where the gender is female and the wealth is poor. So it will be 0.253 plus 0.042. Okay? طيب, can we generalize this? Yes. For every logical expression, we just add the probabilities of the rows that match this logical expression. So another example. What is the probability of a male that has less than 40.5, that is working less than 40.5 hours? We'll just go through the rows and see if it matches or not. Does that one match? No. This one? This one? This one? This one? Yes. It's male and less than 40.5. Next one? Yes. So this one and this one. How about this one? No. This one? No. So the probability will be adding these two values together. Okay? So we can generalize this. Probability of any logical expression equals to the probability of the rows that match this expression. Let's get another example. If I told you what is the probability of female or male who are rich? So female or male that is rich. So which rows? So again, we'll go through the rows and try to match the expression. The expression says female or male and rich. So how about the first one? Does it match? No. Second? Yes. So second matches. Third, fourth, fifth, sixth, seventh, and eighth. Okay. So we will just add these corresponding values. That will be the probability. And any logical expression can be used. We can compute the probability for this way. Okay. Right. Any question about this? This is useful, of course, and we will see how useful it is. But by itself, we rarely do that. But we use it for more interesting inferences. For example, can we compute this probability of male given poor from the table? How, Asma? Tell me first you want to get it directly without writing the expression? Tell me how you will get it.
We'll go through the table.
Okay, is that now a logical expression? Not exactly, right? So we will not be able to just sum over some of the rows here. We'll have to do it maybe in 2 steps.
By the row,
Yes, maybe. Nama? Exactly. We will convert it into joint probabilities. Because what we have in the table is just joint probabilities, right? So this is conditional. It's not direct from the table. We cannot directly get it from the table. So we will convert it into joint probabilities. If we convert it into joint probabilities, we are done. Because we can compute any joint probability, right? Right? So probability of male and poor over probability of poor. How did we know that? How did we know that this is equal to that? Huh? Bayes rule. Bayes rule tells us exactly this. Okay, the joint probability over the the conditional probability. Can we compute these two from the table? What is the probability of male and poor? I think we did it already, right? Male and poor. So this one and this one, right? So it is this number plus that number. 0.33 plus 0.13 over probability of poor. What is probability of poor? Add all the poors. Okay, nicely said. Add all the poors. So we'll add this one and this one and this one and this one, and this will be the numerator, and this will be now the probability that we want. So we can compute it. Type. What if I told you I want probability of poor given male? Can we do it? Or not? How can we do it? It seems like the opposite, yes, but how? So, probability of poor given male. How is it different from this one? So, how about the numerator first? Will be the same or not? Probability of poor, comma male. Okay. Over probability of male. Okay. Type. Let's take probability of male. Okay, we can compute it, right? You will just how will we do it? Probability of male. Add all the males. Thank you. Add all the males. Okay, as A suggested. So that's the male probability of male. Type. How about probability of poor, comma male? What do you mean by comma here? Oh no. No. Comma. What do we mean by comma here? And. That's joint. Joint means and. Okay. This is and. So this is probability of poor and male. And this is different from probability of male and poor, right? No, they are the same, right? They are the same. So this one is the same like this one, of course. The only difference is the denominator. Okay, type. Can we also compute something like this? Probability of poor given male, comma, which is and, less than 40.5. Can we do something like this? How? Can we use Bayes rule? Can we? Can you tell me how now? This is like what? This is like A given B and C, right? Can we compute this probability using Bayes rule? Yes. Probability of the joint probability in the numerator, which is A, comma, B, comma, C. Probability of A and B and C over probability of B and C. Bayes rule is the joint of all of them over the probability of the joint, or over the probability of the conditioned ones. Whatever is the condition. Whatever is the condition. Okay? Type. Now, can we do this here? Can we do that here?
At first, I thought it was A condition B, and then and C. Not B and C.
Oh, no. This is, when we write it that way, that means we observed already B and C. Now we want to compute the probability of A given that we observed B and C. That's how it is written. I got your point now. You thought that it is A condition B and C. No, that's not. So how can we compute this now? To be probability of poor and male and less than 40.5 over probability of male and less than 40.5. Can we compute each of them? Yes. How about the numerator? Poor male and less than 40.5. Where is that? Which rows? Only the first one? No, the first one is female. The first row? The first male row. Okay. This one. Okay. Only? Yes. And how about the denominator? Male and less than 40. It's this one and this one, right? Okay. So we can compute any conditional probability actually this way using the joint distribution. So using the joint distribution, we can compute the probability of any logical expression, and we can also compute any conditional probabilities. We call this inferences because we are observing something, we are given some information, and based on that information, we infer or we guess something else. Okay, so this is making inferences using joint probabilities. Any question on that? Can I erase everything here? How about this one? What's this actually? Is that a probability? That's not a probability, right? This is probability distribution. That's a complete distribution. That's not just one probability. Here we are using the names of the variables, not the outcomes. Okay? Probability of wealth given probability of gender and hours. What we actually mean here is all possible probabilities that match this. So, for example, probability of rich given male and greater than. Probability of poor given male and greater than. All possible values. Okay? So how many probabilities actually are represented here? Yes. 4? Why is it 4? How did you know it's 4? How many variables we have here? 3. How many possible values for each? 2. Then how many combinations? 8. Yes. 8. Okay. So we will have 8 probabilities here. So that's a complete probability distribution. Type the sum of the values, we can compute each one of them, right? And just substitute by a specific value of each variable, you will be able to get the corresponding probability. If you sum all of these probabilities, you will get 1 because it's actually probability distribution. Okay. Yes.
Let's consider like mean and then over wealth.
Oh, sorry. Poor. Okay.
And then mean and then less than 40. Is it the same result than the first one we did?
I don't remember the first one we did. Anyway, what's your point? Maybe it is, but I don't remember exactly. You mean the way that we can compute? Yes, exactly. Yes, of course, yes. But the point here is that this is a complete distribution. This is not just one probability. These are actually 8 probabilities. But each of them will be computed the same exact way we did before. If you substitute, yes, you can compute it. For anyone. Any questions? Okay, fine. Now let's back to machine learning. How is that related to our context? As we said, we will assume that the training examples are drawn from or are generated by a joint probability distribution. But we don't know this probability distribution. If we know it, then classification will be very easy because we can compute everything, right? From the joint distribution, we can get anything. You can do actually an optimal classifier, but we don't know it. So we'll have to estimate the parameters of the distribution. That's the whole story now. So now when we say training in the context of probabilistic models that will use probabilities, it means that training means that we will estimate the distribution from which the training set is generated. And of course, estimating a distribution means estimating the parameters of the distribution. Now, can you give me examples of the distributions that you studied already? Probability distributions. You studied in statistics, I am sure, multiple distributions. Do you remember the names at least? Gaussian distribution, very good. What else? Is that continuous or discrete? Continuous, very good. What else? Gaussian is the same as normal. What do you think? Yes, it's just another name of the same distribution. What else? Poisson distribution. Okay, is that discrete or continuous? I think it was continuous. Okay. What else? Bernoulli distribution. Okay, actually, you will hear about it very soon. Is that discrete or continuous? You don't remember. It's discrete. Any others? Binomial distribution. Multinomial distribution. Okay. طيب. Why do we actually study multiple distributions? Why not one? Yeah? What's the point of having multiple distributions? For what? Why? What is the importance of those distributions? Why do we actually need these distributions? Huh? Because data is distributed differently. Yes, because different data are distributed differently. And let me maybe make it a bit more clear. Instead of saying data, problems are different, or data for different problems are different. So we can model the data in one problem maybe as Bernoulli distribution. And we can model data for another problem as binomial distribution. Okay? Type. How do we actually choose these distributions? Based on what? Based on our experience, knowing about the problem. Okay? And we'll see an example very soon. But these distributions are different. Type. These distributions also have parameters, right? Yeah, for example, the Gaussian or normal distribution, what are the parameters of those distributions? Of Gaussian distribution? Balash Gaussian, the normal distribution. What is the parameter? What are the parameters of the normal distribution? Standard deviation? That's the only one, or actually it's the variance that is usually, or standard deviation. We can say yes, standard deviation and the mean. Usually we say mean first, it's easier. But yes, mean and standard deviation are the two parameters of the distribution. So each distribution has its own parameters. Okay. Now, if I gave you data and I told you this data came from or generated by specific probability distribution. From this data, you should be able to estimate the parameters of the distribution. I think you saw this already in statistics course. You are given some data and you fit a specific distribution on this data. That means you will estimate the parameters for that distribution. And this is what we will also do here. Okay, so we will always assume that our data is generated by a specific distribution. Which distribution? We will choose it based on our knowledge about the problem that we are solving. And learning will mean that we will estimate the parameters of this distribution. Type. Now, we will assume that the data came from a distribution, right? That's our first assumption. Another assumption is that the training examples are what we call IID. What do we mean by that? We know that in training, we use training examples, right? We assume that we have already training examples, right? If we want to classify, for example, whether you will get an A in this course or not, okay? So every student will be like a training example if we know the grades of that student in other courses. Okay, so each student would be like a training example, and we can build a classifier based on the features of each training example. Here we assume that all examples are of course sample, right? Because we don't have all possible examples in reality. We just have a sample of them, right? So we assume that every example in the training set came from the same distribution. All of them came from are generated by the same distribution, same probability distribution. We call this identically distributed. So this is the second I in IID. Identically distributed means that every example actually is drawn or sampled from the same distribution. So if we say that the data came from or generated by normal distribution, then every example that we get in the training set is generated by the same distribution. Okay, so this is logical. Otherwise, it would be very complicated if we assume otherwise. Okay, clear? Now the second one, independent examples. So the examples will be independent. Now let me explain this to you, and that will be the last point in the lecture, inshallah. You studied independence in we will take just a couple of minutes, Sophia. Okay, don't worry. You studied, I think, independence, right? What do you mean by two events that are completely independent? Very good. The probability of one is not affected by the other. Or maybe in a simpler way, if I know that one of them happened, that will not give me any idea about whether the second will happen or not, or what's the probability of the second happening. They are completely independent. Okay? Type. Let me give you an example here. And that's probably one of the classical examples that you use in statistics. The example of the bag that has colored balls. Okay, let's say that we have 6 balls in the bag. Each one has a color, and we know how many red and how many green and how many blue. Now, let's say that the first event is taking a ball from that bag. Okay, let's say that it was red. Now, the second event is taking another ball from what is remaining in the bag. Are these two events independent or dependent? Did I? I didn't say that I put it back. I said I took the first one, then that's the first event. Then the second event is taking the second one from the bag, from what remained in the bag. Are these dependent or independent? Dependent, of course, right? Because knowing the color of the first one will affect the probabilities. That's the other probabilities, right? Fine. If I told you now that after I took the first one, I put it back in the bag, now the two events are independent, right? Is that clear? Okay. Fine. So it can happen that events are dependent and events might be independent. Another example. If we are looking at words in text, okay? If you are reading the words and you saw a word river, okay, will that affect your guess of what could be the next word or not? Yeah, for example, can I say, can you think the probability of seeing the word Qatar after river is high? Right. How about the probability of seeing the word Nile after river? It's high, right? So that means that the sequence of words in text are dependent or independent? Of course they are dependent, right? Of course they are dependent. So in real life, events might be dependent or might be independent. Actually, most of the events are dependent. Most of the events are dependent. But here we will assume that seeing the examples which are actually events, right? Each example is like an event. We will assume that they are independent. They are independent. Of course, this assumption, as you saw from the examples, is not 100% perfect. Actually, usually it is the opposite. But in probabilistic modeling, it is good enough to get good predictions. So, and it will make our life much easier to assume that the training examples are independent. So this is the meaning of IID, or independently and identically distributed. So when we say that the sample that we have are IID, that means that all the examples or the samples in that sample are generated by the same distribution, and they are generated independently. Okay? We'll have to stop here, and inshallah we'll continue next time. Assalamu alaikum wa rahmatullahi wa barakatuh.